Good morning again, everybody, and welcome. Today is the third week, actually, of this class, and I want to bring your attention to an important event that is happening next week. And basically on March 11th, which is a Thursday, you will have a review that is going to be open for you guys to go through it, okay? That prepares you for the exam. This review is graded though, okay? Regardless of your score in it, as long as you take the review, you're going to get the full mark for it. So let's say, for example, it's out of 120 points, and you take the review and you score, let's say, for example, 20 points because you're trying to prepare for it. Actually, it's more than that, more than 120 points. But the point being in here is, regardless of what you actually score in the review, you're going to get full credit for it. The only way you're not going to get full credit for review is by not taking it, basically. At that point, there is nothing I can do for you. The point in here is that to encourage you to go through basically the materials that we covered from chapter 1 until chapter 7 by then, okay? And that help you basically prepare for the actual exam. The exam actually will be available on Tuesday the 16th, okay? And I will make it available. I know this is a reg meet class, meaning that you're expected to be regularly in this time. So if you're working, you really have to take time for the exam because this is a reg meet, as if we are meeting in person to do this class. And at that time, there is no excuse for being out for work or anything like that. If you look at the campus. However, I'm going to try for some leeway to give you some room. I'm going to try to start the exam a little earlier than the actual class and finishing during the time of the class. So if you really have to be at work by 9 o'clock, you can still take the exam, be done with it, and show up to your workplace, okay? So that's the only thing I can offer you at this point. So hopefully you guys take the review and be ready for the actual exam. You need to know that the actual exam is timed, meaning if you start it, there is a time limit where you have to finish it. You cannot say, oh, the window is open, let's say, for example, for 5 hours, therefore I have 5 hours for the exam. No, you only have an hour and a half for the actual exam. So once you start it, it doesn't matter what time you're going to end it, you're going to be given an hour and a half, provided you did start it before 9 o'clock. Now, if you started at 9 o'clock, it doesn't matter. You're going to be cut off at 10:30. Okay. So by that time, you need, the latest you can start the exam to have the full time for you to take the exam is 9 o'clock in the morning. So that's basically what I'm talking. I know some of you are not right now live, and some of you are going to watch this video later. But you need to understand the process. And if you have any questions, please let me know. So the key thing first is the review coming on Thursday next week, not this Thursday. This Thursday is what, the 5th or the 4th of the month? It's the 11th when the review will be available, okay? So a week from this Thursday. Does everybody understand what we need to do? So please take the review at least once, so that to get full credit. Now, the credit you're asking, where is that supposed to be? It's supposed to go toward your participation grade, okay? To be part with the participation grade. So that means you're doing the things you're supposed to be doing to pass this class. That's basically what it is. Everybody understand? Good. How many questions in the exam? There will be timed enough so that you basically have enough time to submit your work and review it, okay? Usually, typically, it's about a minute and a half per question, okay? So you can figure out the math in there. Usually, it's about 60, 70 questions, okay? And it's coming off of a data bank. So basically, if you take the exam, of course, you will only have one chance at it. But if you take it again, you're going to have a completely different exam. So basically, the bottom line is if two people are taking it, they don't have necessarily, actually, they don't have the same exam. Okay, so that's the power of the review. That's why you really have to do the review, because then you cover all of your bases, regardless of what form you end up with. You should be well in doing your exam. Does this answer somehow your question, Corin? Okay, good. Okay, so let's finish. I know we didn't finish last chapter. Unless you guys have different questions, which you're welcome to send them, please do, okay? And I think there is another assignment today, this week too. So please take care of all of these assignments in addition to the participation, so that you're, because this is a fast-paced course. I mean, we're covering everything there is in physics and physical science actually too. Okay, so let's, unless you guys have another question, we're going to jump into where we left off last time.
I have a
And it's,
question. It was
yes.
regarding, I think, last week of the discussion. I noticed that the chapter 2 discussion, and then there's a chapter 2 part 2. The same video is linked within those two sections. So I'm wondering if I'm still gonna get credit because I did both items in the chapter 2 discussion on the initial chapter 2 discussion module.
Okay, the point of the participation actually is so that you guys show up in class and basically do the things you're doing. So since you're in the class, usually there is no problem with it. I'll go through it, and if you don't find the full credit as expected, and this is true for everybody, by the way, not just for Marianne, please let me know, okay? Send me a message saying, hey, you did not credit me for what I'm supposed to have, and it should be corrected, okay? Yes, Marianne? So if you see
Yes,
that you're
thank you.
not for it, let me know. Okay, so this is basically where we left off last time, and basically we're still dealing with chapter, what is it, 4, okay, from the book. So again, we discussed this one, I think, to some extent, the fact that the weight that we experience is actually the reaction coming from where we're standing, and that's how we use basically the normal force to measure the weight. Case in point in here, you don't feel weight at all, although you still have weight, you have mg, but you don't feel it. That's the only difference. It's not like you're weightless, you don't really have any weight, but you don't feel your weight because of the fact that, in other words, the gravity, the force of gravity between you and the earth still exists, just because you don't feel it, okay? So again, we discussed this, I think, to a lot of detail, and I think I mentioned that way back when we started class, and if you guys have any questions, please let me know. Projectile motion is an example of a two-dimensional motion, that is motion that is happening both in the x-axis and the y-axis in the same time. You take a rock, for example, and you throw it, and that is a projectile, okay? So what's going on in this case is the rock will follow a path, and that path is a parabola. So what's going on? In the x-axis, it's just moving straight line, okay? But in the y-axis, it's moving up, but because of the gravity, it's pulling it on down, so it's going to slow down until it stops completely and then starts falling. Meanwhile, it's dragged. So technically it's going up and down, okay? But it's dragged in the forward position in this up and down motion, okay? And the actual path is a parabola. So that's basically how this can be described. So if you throw a rock, if I throw this object in here up and down, this object will still go up and down. But if I throw it at an angle, it's drifting while it's doing that vertical motion. It's drifting in the horizontal direction while it's going up and down. So that is actually what the projectile motion. So in the sense, it's still accelerated, gaining that 10 meters per second for every second it goes through, meaning the distances in the y direction are increasing at that rate of 1/2 the g, which is 10 meters per second, times the time squared. That's why you see this distance is much higher than this one, which is greater than this one, which is bigger than this one. Whereas in the x-axis, the distance is the same. This point and this point are spaced as much as this point and this point, which they are spaced as much as this point and this point, and so on and so forth. So this, what I'm going to say in here about this motion in here is that this is uniform, okay, in the x-axis, whereas in here it's uniformly accelerated. Accelerated. So that's basically what the projectile motion is. And what is the acceleration down in here? It's actually g, which is equal to 10 meter per second, or 10 meter per second squared. And here there is no acceleration, is equal to 0. Hence we call it uniform motion. It's the same thing. The velocity doesn't change. So this is basically in a nutshell what this is. So constant motion horizontally means uniform. So if you see this word somewhere, and the questions or something, that's exactly what that means. Accelerated motion, but it's not just any acceleration in here. This acceleration is constant. That's why we dress it usually with the word uniformly accelerated, meaning the acceleration doesn't change. It's always 10 meters per second per second. Whereas in the first case, the horizontal motion. So this combination of these two motions is what is a projectile. So a projectile is an example of a higher order motion. It's a two-dimensional motion. And like, for example, a rock, if you throw it up and down, is going to be a one-dimensional motion. It's going up and down, that's it. But this one goes up and down in the same time, drifts in the horizontal direction. So again, this is an illustration of that point. This points in here, they're equally spaced. This distance and this distance and this distance are the same distances because it's uniform motion. Whereas this distance, clearly you see it's much, much less than this one. And this one is actually bigger than this one, which is bigger than this one, which is bigger than this one, which is bigger than the first one. So this is uniformly accelerated. So again, that's the projectile motion. So this is how you can visualize it. The velocity can be broken into two components, this velocity in the horizontal direction and this velocity in the y direction. As you can clearly see, the velocity in the y direction shrinks until at some point it's gone to zero. So the y component in this case has nothing. The vertical component, there is no velocity. This is at the peak. This is when we reach the highest point in the motion. And then it reverses actually. It was pointing up, now it's pointing down. And now it's even pointing bigger down. So it's going to grow, then shrinks, then vanishes, then reverses, and then is going to increase when it's reversed. Whereas the x component stays the same. It doesn't change. Okay? The velocity here, this is a property of a projectile. If there is no air resistance, this velocity and this velocity are the same. So you throw a rock with a certain velocity, it's going to come back with the same velocity. And this is basically how catapults work, and this is how old weapons basically using rocks work, and so on and so forth, okay? Any questions about how to describe this motion? Okay, in terminology, and this is probably, you see this terminology for projectile motion, this distance from this point to that point to the end, basically, not just in here, to this point, is called the range, okay? The time for it to go up and down, basically, the entire time is called the time of flight, or the, while it's suspended, okay? So the entire time is called the time of flight. Again, these are just certain terminologies. The key question that you probably will see also is, what is the maximum range I can achieve? Well, the maximum range that you can achieve is a balance of two things. If you put all of your vector, this one, the velocity in here, so that means you have nothing in here in the y direction, then that means you have the greatest velocity with which you can move. However, if you put your cannon right with the horizon, the cannonball will just travel right immediately and smash into the area. So it's not going to go far, okay, because of that immediate contact. Or, so this maximizes the velocity with which you're going to go. This, on the other hand, if you cancel this one and you dedicate all of this velocity here, so that means that this will go very, very high, much higher to this point and come back, okay? So this is going to be the highest that you can do. And this maximizes the time of flight. Actually, it's going to stay suspended in the air for a long, long time, longer than this one, okay? This one will go in zero flight, basically, because it immediately hits the ground. Whereas this one will have the maximum flight. So this one will have no range. This one will have no range because it's going to fall on the head of the person who's trying to throw the cannon. I mean, throwing the cannonball through the cannon. It's going to fall on that head. You don't want that. You don't want this. So you want something in between. And it's actually the angle between 0 degrees and 90 degrees, which is exactly 45 degrees. Okay. So if you're in the military and you're trying to wonder what's the best angle with which to aim so that I can hit my enemy, well, the furthest I can go into their land, that is the angle with which you hit, provided there is no air resistance and and all of the conditions are right. Usually it's slightly less than that with the air resistance and things like this. Okay, so that's basically typical question that you might encounter. So the maximum range is for an angle, I missed the N in here, of 45 degrees, which is not 0 or 90, somewhere in between, exactly in between, middle points. Okay, good. So this is in a nutshell the discussion that we typically have. This is actually what I was talking about in here, the ranges. Look at 15 degrees and 75 degrees. If I add 15 plus 75, I get exactly 90 degrees. They're complementary angles and they have the same range. Okay, a 30-degree angle and a 60-degree angle, if I add 30 plus 60, that too is 90 degrees. They too have the same range. So two complementary angles, they will have always the same range, whether a small angle or a big angle. As long as they add up exactly to 90 degrees, then they have the same range. And in this case, out of this 1, 2, 3, 4, 5 projectiles, the biggest range is exactly 45 degrees. This distance, that's the longest, the maximum range. The furthest you can hit this projectile is at an angle of 45 degrees. Not less than that, not more than that, exactly at 45 degrees. Because if you throw it at 0 degrees, it's going to go here. If you throw it at 90 degrees, it's going to come back to the same point, because 0 plus 90 is also complementary angles. Okay, so that is the point in here. Is this point clear? Okay, at least some nodding heads. How about other people? They're good with this idea? You can't see the chat while I'm sharing. Okay, very good. Thank you very much. Two more people confirm this stuff. Okay, so again, this is the example what I was talking about in here. The cannon ball in this case, if it's emitted with a velocity of 40 meters per second, it doesn't matter which angle you throw it at, it's going to lose the velocity in the this is the vertical velocity. Okay, we're not talking about this component that makes it drift in this direction. Okay, so this is 40. After 1 second, it drops by 10 meters per second. After another second, it's going to drop by 10 meters per second. After another second, it's going to drop by 10 meters per second. And this distance actually is also the same 1 second, because it drops, it loses that last 10 meters per second till it stops. Then it reverses path. Is going to increase from 0 to 10 meters per second in the next minute. So if this was a second, so this is the first second, the second second, the third second, the fourth second, the fifth second, the sixth second, the seventh second, and the 8th second. This entire flight will take 8 seconds to go from, so this is the time of flight. If this is in time in seconds, okay? So basically, I'm losing initially 10 meters per second until I reach the top where all of it is gone. Stop and reverse path, okay? And again, gain that 10 meters per second in the second half of the trip, and fall back with the same velocity that I started with, okay? And now there is a perfect symmetry in this path. As you can clearly see, there is a one-to-one correspondence between these two, right in the middle where things happen in here. So the time of flight is actually just twice the time of reaching the maximum, that's all, okay? Because this is 1, 2, 3, 4 seconds, and coming down is another 4 seconds for a total of 8 seconds, okay? If you throw a rock fast enough, okay, this rock will be trying to fall, but because of that velocity will continue and basically orbit the Earth, okay? So that's how you put satellites into orbit, of course, right around the Earth. I mean, if you are within your high, you have to really throw the rock very, very fast, and you can calculate that speed, how fast you need to. I mean, there is not enough energy for you to do it. So if you throw it at a higher distance point in here, and then it's going to stay in orbit. So that's basically how it is. So in other words, it's trying to fall to the Earth, but it has that velocity in the horizontal direction, So it's going to go with the sum of these two velocities, which is somewhere in between. And that is like a projectile, really. It is a projectile, except it never reaches the ground, because if you think of the Earth like this, you throw a rock from a distance, it's going to fall if you don't have enough velocity on it. So that is a projectile. If you throw it with a higher and higher velocity, it's going to reach another point where it reaches the ground. So, but if you throw it with even higher velocity, it's going to fall below the horizon. But if you throw it with even a higher and higher force, you're going to reach a higher and higher velocity. You're going to reach a point where that basically it always catches itself before it falls. So that is basically the concept of how satellites move. Okay. So this is again the illustration. If you want to reach that speed, you have to send it within 8 kilometers basically per second, because it's going to drop. So it needs to travel 8,000 meters in here to drop that 5 meters. So it's going to catch itself before falling, basically. Okay. If you throw it with a higher velocity, it's going to escape the Earth completely. So if you give it just this velocity with which basically it's going to compensate for its fall, it's going to stay in orbit. But if you throw it even more force than this, more velocity than that, it's going to ultimately spiral out of the path of the Earth and it's going to leave the Earth. And that is what we call the escape velocity in this case. Again, this is an illustration here of what I was talking about in here. If you just drop it, as the ball leaves the ground, it will fall 10 meters, 5 meters below the dashed line. For every second, it's going to drop. The first second is going to drop 5 meters, because remember the formula says 1/2 times g, and g is 10, times 1 second squared. So in this case, it's going to drop by 5 meters, okay, after 1 second. If it catches itself before falling, so after if it's just in here, it's going to drop to this point and this point. But if it catches that 5 meters while it's still in path, so it's going to basically stay in orbit. Okay. Again, this is an illustration of the example of what we were talking about. Okay. And this is what I was talking about. If the satellite doesn't have a lot of velocity, it's going to fall somewhere in the ocean or on Earth somewhere. Okay. But if it has this 8 kilometers per second, it's going to retain that basically path, because it's always moving just enough to compensate for that fallen 5 meters, okay, per second, for every second. It does that for every second. For most of the times, our satellites are way above the atmosphere, okay? So the space shuttle is about 150 to 100 kilometers, depending on the applications, what they want to do. But for the GPS, is actually, you need to be in the thousands of kilometers. Okay, actually, you can calculate how far they need to be, because a GPS, global positioning satellite, is needed to be in such a way that it stays in its orbit all the time. And if you're looking at a GPS right now above your head, that GPS needs to stay there as the Earth is spinning, for your phone to lock on it, for your cell phone to lock on it too, so that your watch and your cell phone and everything else, so that it determines and pinpoints where objects are in the Earth. So this is a very important application for the GPS system, because you would want that positioning to be always pointing to where you are in space. Okay, so that is basically the point in here. So they need to be very far. You can find their radii, because as we were talking about in here, if it's close enough, it's going to need to be moving super fast. Okay. So it's going to move faster than the Earth, but you want it to be in such a way, as you're looking at that satellite in here, as the Earth spins, the satellite also moves with the same thing, but it's moving on a bigger curve than you are, because your radius in here on the Earth is only 3,600 kilometers, whereas this one is moving on a very large distance in here to keep up with you. It's moving this arc distance, whereas you just moved this much arc displacement on the Earth because of the Earth spinning. So in this case, it needs to move with a higher velocity to keep up with you, basically, to make sure that you are there. For that, we need to put it at this higher distance in here, okay? So that's basically how this works for the GPS system. I hope that you guys completed this assignment because that's part of the stuff that is due actually for this one. And this is what we were talking about, the elliptical path. All of the objects described in elliptical, actually all motion of all of the celestial objects are one of the so-called conic shapes. And conic shapes, if you take a cone, a 3D cone, not necessarily a two-dimensional cone, you take a 3D cone and you cut through it. If you cut right in here, you're going to end up with a circular path. If you cut right in here, you're going to end up with this elliptical path. If you cut right in the right angle, you're going to end up actually with a ellipse or a parabola. So you're going to end up first with a parabola, then you're going to have an ellipse, and all of the paths are actually conic shapes. And this is basically what you did last time on the activity. Peter, were you saying something? Because I saw something pop up in here. Sometimes when you guys move something and your microphone is off, Zoom will change location. I have no idea if you guys were trying to say something or. Okay, this is again what we were talking about earlier for the escape velocity. You need this minimum velocity of 11.2 kilometers per second to escape the Earth. Okay, not the pull of gravity of the Earth. It's always there, okay, even if you are at infinity, but so that you don't stay in orbit. Okay. So if you have this velocity, your motion will be spiraling out of the Earth, okay? And you can go. At some point, you will be the pull of the Earth will be negligible, okay? So think of the Perseverance the other day that landed on Mars. It needed at least this much velocity to escape the pull of the Earth, okay? Actually, it needs higher than that to actually reach Mars. But the point in here is that's how satellites, I mean, the spaceships work and everything else, so that you want to deploy them outside of the Earth and send them somewhere else. So this is the minimum escape velocity. If you ever watched the movie Martian, where he got stuck on that Mars planet and he wanted to leave it, and he was doing calculations, he was trying to get enough fuel basically to reach the escape velocity off of Mars, which is less than this escape velocity, about half this much. So he needed less fuel actually to get off of Mars. And then at the end, he did not reach his rescuers enough. So he started, I mean, the first thing he started throwing stuff because that was going to slow him down basically, and not gain enough velocity through the initial acceleration with how much fuel he had basically. So that is basically the concept of escape velocity. So if you ever get stuck on Mars, you need to know about this stuff in here so that you escape it, okay? Or any other planet for that matter, the moon or whatever you might choose to go to, okay? You have to have a plan of a return, otherwise you're going to be stuck there. Okay. So again, we were able to deploy all kinds of objects outside of the Earth because we learned about this thing in here, the escape velocity. And the key thing in here, and this is probably one of the questions you might encounter in some of the exams, is the escape velocity is basically for the Earth is 11.2 kilometers per second. This is a good thing to know, okay? So this is the entire chapter in a nutshell. There are no questions in this chapter because we covered it last time. The question that you're working on or you worked on, that is actually part of this stuff. Okay, any questions? Otherwise, we're supposed to do for a new chapter now. And the new chapter is on fluid mechanics. Okay, so let's share the screen in here. Chapter 5, okay? One of the ideas that we need to, are you guys looking at chapter 5? Yes? Okay, good, thank you. So basically, fluids, like this nice coffee I've been sipping all morning today. Hopefully you guys have had some already. If you're not a coffee drinker, good for you. Anyway, we want to describe fluid, okay? So we have a fluid, it's sitting in front of me, and I want to come up with a description for it. Excuse me. This is common to all physical science, actually, not just in physics, but physics emphasizes on measurement, okay? So in other words, if I come up with a concept in here to describe this fluid, here is a fluid, for example, and I want to describe, let's say, for example, it's minding its own business, calm. I don't see anything moving in it. So what I'm going to call this thing in here, I'm going to call it's in a static position. It's not moving. It's not dynamic, okay? So in this case, how can I describe it? Obviously, if I have this coffee and I bring another cup of water in here, I see that the consistency is slightly different between the two. As a matter of fact, if I bring honey on the other side, it's clearly different than the first two. If I bring, for example, oil, it's a different structure in here. So one of the quantities that we use in this case to measure or to distinguish between two different fluids is the concept of density. And what density is, by definition, is the amount of mass divided by the volume it occupies, okay? So that is actually numerically what I can do. I can take this coffee and weigh it. Weigh the cup first, because I can't really remove the coffee from the cup and put it on a scale because it's not going to work. Take the cup empty, put it on the scale, see how much it weighs, pour the coffee in it, and see how much now it weighs. So I know exactly how much this thing weighs, okay? Now I can also measure the volume of the cylinder. If I use formulas, math, or I can actually use liquid in here, fill it with water, for example, and so how much is going to occupy on a scale, for example, how many liters that is. Now I know the density of this fluid. If I want to compare this one to another density, for example, of oil, then I will have probably different numbers. Good number to remember is the following. 1 liter of water weighs, or actually the mass for that is 1 kilogram, okay? So the density for water is exactly 1 kilogram per liter, okay? This is a nice round number. I mean, who cannot remember 1? Okay, 1 is a good number to remember. As a matter of fact, it's also 1 gram per cubic centimeter. It's only complicated when I'm talking about a cubic meter. It's a ton, or 1 metric ton, that is, 1,000 kilograms per cubic meter. So think of this room in here. Open your eyes, your hands like this one in here, okay? A little bit like this. That's about a meter, okay? If you position it this way, that's a meter squared. If you move it in depth, that's another meter. That's a meter cubed. If you fill this space with water, that's a ton. That weighs as much as your car outside, okay? Metric ton, okay? So that is how much the density of water is. If you take oil, on the other hand, it weighs less for the same cubic volume. So there is a distinction between the two. I know I'm dealing with oil if I measure its density is less than that of the water, okay? So this is density is one of the ways of measuring things in here. The other thing also that we can use is the pressure. The concept of pressure is really the force divided by area. Obviously, if I push on an object, now everything is moving. I can put it on this side. If I push on an object, I exert a force on it. Okay, I'm pushing my hand in here. But this is the contact surface in here in this case. So I exert a force in here. Whereas if I take a sharp object and exert the same force, there will be different impact on here. There is a different effect in here with the same force. This one looks pointier and actually will hurt more for the same force. So if all you can afford is 10 newtons, you can do more damage with 10 newtons if you make the surface of contact less. Hence the concept of pressure, okay? So pressure, how much pressure fluid exerts, that is a key component to describing fluids also. As a matter of fact, if I go inside a fluid in here, I feel the weight of the fluid from above, okay? If I go deeper, I will feel more pressure, okay? So depending on how far I am in a fluid, I will see different pressures. Again, so we have 2 ways now of describing a fluid. One way is density. The other one is pressure. pressure, which is force over area. Okay, so these are the two basically that you are sitting in your room right now. I am sitting in my room. Everybody's probably, somebody else may be laying on his or her bed, for example, or on a couch or something like that. There is a tremendous pressure on your shoulders right now as we speak, that of the air above us. And that amount is 100,000 newtons per square meter. That's a lot of pressure, okay? But we get accustomed to it. We're used to it, okay? And the air is a fluid too, okay? We got used to it. Our bodies are adjusted to it, okay? If we happen to land on Mars, for example, the pressure there is about 1% or about 2% that of the pressure here on Earth. So your body is not used to it. So if you happen to be on Mars without any proper suits for it, actually your inside will come out. You're going to explode, okay? Because of tremendous pressure inside versus the outside pressure, your fluids try to basically come out of everywhere. If you go on Venus, for example, where the pressure there is about 90 times the pressure on the atmosphere, you're going to be crushed actually because of the weight of the atmosphere on Venus. Again, we are used to this 100,000 newtons per meter squared, and that is because of our daily experience. So the units for pressure, usually it's called the Newton per meter squared, but people in honor of Mr. Pascal, they give it the unit Pascal. So from now on, you're not going to be hearing me saying the word Newton per meter squared, but I use Pascal. As a matter of fact, there is another unit for the pressure, at least here on the Earth. We use the atmospheric pressure as one unit. So we're sitting in 1 ATM, 1 atmospheric pressure, or 1 bar, basically. So that's really how we use the unit also for the pressure. So there are about 3 versions of it: Pascal, bar, and atmospheric pressure, ATM. Okay, so if you hear the weatherman talking about the pressure rising and 900 and something bars or something, and we even use the millimeter mercury. Okay, the weatherman says the mercury rising or the mercury is dropping, the pressure is going up and down. Okay, so that they use that, and they use actually a different unit also. Okay, so again, these are concepts. Then we're going to talk about buoyancy, and buoyancy is actually a concept that basically, if an object falls in an object falls in a water, I'm sorry, or in a liquid, it's going to experience lift force that is coming and pushing it upward, and that is actually coming from the fluid itself, from this pressure. Okay, because as the object drops in a fluid, the level of the fluid actually changes because of this displaced volume of the fluid. So it's going to rise by this much, depending on this volume. So if you put bigger object to much larger object in volume, that is, not in mass, the mass could stay the same, but as long as the volume changes, you're going to displace more fluid. So that bigger object will experience a bigger lift force, an upward force, and that force is a so-called buoyant force. Okay, that's what Mr. Archimedes came out of his shower when he discovered this one, and he said, basically, I found it, eureka, eureka, eureka. Okay, running in the streets of Athens, basically naked from the shower, talking to people. I found it. And he came up with this principle of buoyancy. Okay. Of course, you're imagining the scene right now, a naked man running in the street and found it. So, okay, don't do this experiment at home, okay? You'll be arrested for it, okay? For indecent exposure. Okay, Archimedes' principle, that is the point I was talking about, okay? And then pressure in a gas, that's an extension of the other topics. The atmospheric pressure, I already mentioned a few things. Pascal principle tells me how the pressure is distributed in a fluid in general, liquid or water, and it's going to be the same everywhere on the same level, okay? So that is basically what the buoyancy in a gas. And then we're going to talk about Bernoulli's principle, or Bernoulli's equation, which is really how fluid moves from one point to another point. So all of these things can be thought of a fluid not in motion. This is called hydrodynamics, the fluid in motion, okay? That explains a lot of things for us, how planes take off and things like that. Isn't this promising, this chapter? Yes? Okay, so density, it's an important property of materials, solids, liquids, and gases, measure of compactness of how much mass in an object occupies, and lightness or heaviness of material. Okay, you don't need a lot of stuff to feel that this is more compact than this one. Okay, you can actually put them in your hand, and your hand you will tell you that this is denser than this one. Okay, this is lighter. So that's basically what density measures. What you need to know is that density doesn't depend on the size of the object. Okay, whether the object is super big or super small, it has the same density. Because super big object will bring, yes, a bigger volume, but also bigger mass, so that the ratio stays the same of mass over volume. Okay, so the fact that you change the amount doesn't change. As a matter of fact, density is a signature. What happened to my pen? Did I lose it? No, here. The signature of the object. So density tells a lot about the object. For example, if I look at the density of the Earth is about 5.5 grams per cubic centimeter. I know that the Earth is made up of a lot of rocks and metals and things like that. So that's basically why the Earth has this density. If I look for another object, for example, the density of Jupiter, it's 1.3 grams per cubic centimeter. So it looks like Jupiter doesn't have as much rocks and as much iron, as much nickel as the Earth does. Doesn't have as much metals and rocks as the Earth is. As a matter of fact, this is a gas planet. It's made up of mainly gas, super dense gas though. And this one is a rocky planet. That's how we know, okay? Just from the density. You don't have to go there and look for rocks on Jupiter. You're not gonna find much, at least all the way to the core. I don't know what's going on inside. Nobody knows, but that's basically the bottom line. If you look at the density, for example, of what is it? A Neptune cube. That's actually less than that of the water. Remember, the water is 1 gram per cubic centimeter. So if you take Neptune and put not Neptune, I'm sorry, Saturn. If you take Saturn, this is Saturn, by the way. If you take Saturn and put it on an ocean big enough to contain it, basically, Saturn is super big, much bigger than the Earth is. But if you put it in an ocean, Saturn will float. It's not going to sink because its density is less than that of the water. Whereas Jupiter will actually float, will actually sink, okay, just like the Earth does. But the point being in here is you can tell a lot about the structure of this planet just by looking at its density. There is no rocks or metals inside the Saturn because of its low density, basically. Okay, so that's basically in a nutshell. So you can tell a lot about something just by looking at its density. If you look, for example, at Mercury, its density is 5.4 grams per cubic centimeter. So it has a lot of rocks and also metals in it. So just by looking at this thing, isn't this nice? If we can measure somehow the mass of an object and measure its volume, we can know a lot about it. So this is what I said before in the introduction. Okay, and the units for it is in grams per cubic centimeter or kilograms per cubic centimeters. So these are the units for it. Okay. That is basically how we use the units of the density. Sometimes we use a kilogram per liter, but that's kind of because 1 liter is 1,000 cubic centimeters, so, or 1,000 liters also is a cubic meter. So most of the times, those are the units that you will see me referring to. Okay, how many? What is the how many kilograms cubic? How many grams per cubic centimeter inside a kilogram per cubic meter? It's 1,000. So that's a conversion factors if you ever are going to be doing math in this class, so which is usually not. Okay, the weight density is similar to the density itself, except we don't use the mass in the numerator, we use the weight. This is usually doesn't tell us a lot about objects, especially in the outside of the Earth. This is good actually for daily applications. And the pound per cubic feet is an example where this thing is. Okay, so this is the weight of an object versus how much space it occupies. Okay, This is not common in the scientific community. The first one is. This is probably you'll find it in Home Depot or something. Okay, which of this has the greatest density? 1,000 kilograms of lead. 100 kilograms of lead, 100 kilograms of water, or both have the same density, or none of the above. You need to know that lead in this case is much, much denser than water. Because you take lead and you put it in water, it's going to sink. That's how you can tell. Had it been the other way around, if you put oil, for example, on water and wait until the equilibrium comes into place, because all of these things are talked about when everything comes to a static position, you will find that the oil will float above the water, okay? That's why you see after rain, at least here in Southern California, when it rains, you see, look at the ground, you see all of these beautiful, basically colors coming from the reflection of the light because of the fact that the oil is floating above the water that is below it in the rain, and it forms this beautiful rainbow structure just by looking at the water because of the oil on the ground, okay? And we're going to talk probably sometime in the future about these things in there. Okay, again, I define the pressure as the force divided by the area. We use this unit probably again in Home Depot and places like that, but this is the SI unit. This is the one that is used by the scientific community. And in honor of Mr. Pascal, we use the PA for Pascal. So that's what I was saying earlier about the atmospheric pressure. It's about 100,000 or 1,300 Pascal. If you want to, it's a Newton per square meter. This is the atmospheric pressure you and I live on a daily basis. This is what we mean by 1 atmospheric pressure. Again, pressure by force per unit, and it's depth dependent, depending on how far you are in the fluid. Of course, it's a force exerted on the object from everywhere, okay? And it's the same pressure on the same level. So this point in here is the same pressure, and this point in here, it's the same pressure, but it's more pressure because there is more weight in here than this one, than this depth. That's why if you puncture a container in here, it's going to come up with higher velocity, okay? And this one, it's even more pressure as you go deeper, and the fluid will come out even at a higher velocity than the first two, because pressure depends on the depth. The deeper you are, the more pressure, because the weight of the above fluid, basically, that is how you can explain this thing in here. Okay, the weight per unit area, basically, because the weight itself is a force. And when you divide it by the area, it cancels out and it becomes a Pascal. Okay. So again, we talked about this one, and this is basically the point that, so the liquid pressure is the weight of the density divided times depth. So if you want to find this expression, so the pressure itself is equal to the weight density, meaning it's the density times our old good friend G. That is what the weight density is. Because the density itself is mass per volume. The weight density is mass times gravity. That gives me the weight divided by volume. So that is our density times the old value G, which is 10 meters per second, by the way, on the Earth. Okay? And times the depth. In this case, that gives me the pressure. And the pressure is in Pascal. Look at this experiment in here that she's holding. The fluid level is the same regardless of the shape or the area that you have in there, because the pressure is the same on the entire level. So the fluid cannot go imbalanced, although you have a bigger area on one side than the other side, because it experiences the same pressure. So it needs to stay the same level everywhere. So this is actually the principle that we're going to talk about it later on, I'm sorry. And I mentioned actually briefly before. So again, the force of gravity acting on the water, that's how we do water towers, again, because they come up at higher pressure. And that's why when you turn a faucet at home, you're going to get the water with higher pressure because it's coming already with that much one. Otherwise, you need a pump, okay? Short of that, you need to pump the fluid to your place so that you can get a high enough pressure so that it's transferring. So if you don't want to, this is a natural pump. So again, this is the buoyancy. I hope that you guys go through these exercises and try to understand them. And if you have any questions, please let me know too. Okay, we have 72 slides today, and I'm hoping to cover enough of them. So again, the buoyancy is basically the difference in pressure between the upper, because this point sits at a higher level than this one. There is a pressure in here, and there is a pressure in here. And I was arguing that the pressure depends on the depth. There is more pressure in here than in here. So the difference in pressure in here is what gives you that lift. Okay, that is exactly what this buoyancy is. If you take an object that is super flat, it has no volume, it's not going to experience buoyancy. So you should put it anywhere, it should stay where it is. But as long as it has a finite volume, it's going to experience this one in here. And as a matter of fact, you calculate how much pressure it is, the force it is going to be equal to the displaced fluid. And that's basically what the buoyancy in this case is. Buoyancy is this force, the net force, if you wish. So this is the force of buoyancy. Sometimes it's referred to as buoyant force. Okay. So Archimedes' principle, discovered by Greek scientist Archimedes, relates buoyancy to displaced fluid, states that an immersed body completely or partially is buoyed by a force equal to the weight of the fluid that it displaces. Okay, applied to gases and fluids. This is basically the principle behind boats. Okay, if you take a piece of iron, let's say, for example, a boat that weighs 40 tons. Okay, this is a small boat, by the way, 40,000 kilograms. Okay, and you compact it, you make it into like an object, and you drop it in water, it's going to sink. And the ocean is going to sink, because the density of iron is about 7,800 kilograms per cubic meter. Okay, and the water is only 1,000 kilograms per cubic meter. So this is water, and this is iron. So if you put iron, 40,000 tons of iron, 40 tons of iron, 40 tons, that's a very small boat. It's not that big boat at all. It's probably a small thing. If you put that and you put it in the ocean anywhere, it doesn't matter. It's going to go to the bottom. It's going to sink. So what you do in this case, you take this much iron and you shape it into this shape, basically. Okay. This is a cross section cut from it. Okay. The whole boat needs to be I mean, it needs to be nicely basically containing the space in here, okay? So that there is an empty volume in there. Now, if you put that much iron in here, basically, it's going to displace the ocean by a small fraction that is equal to its own weight. So gravity is pulling on it, but the displaced fluid, this buoyant force in here, is pushing back on it, and the boat will stay afloat, okay? So in this case, yes, the density will try to pull it down, but there is a displaced fluid, a big enough fluid from the ocean that is going to keep the boat from floating, okay, and it's going to stay afloat. So again, this is basically the measurement of the buoyant force, and this is how we do it. Fill a beaker to the, or whatever, container to the brim, okay, and then put an object in it. The first thing you notice is that if the object was measuring, for example, 3 kilograms in here, you notice that its mass is less now because it's pulling less on this spring because it's being pushed up by this buoyant force. And contain the liquid in here that was pushed out, and you will see exactly the missing number, 3 minus 1 is 2, and that went into the weight of this fluid, okay? So the buoyant force that is subsiding, it's still, gravity is still 3. If it was, let's say, for example, it was 3 Newton in here, so it's still 3 Newton in here too. It did not change. So this object gravity, the pull of the earth, did not change, but it's being pushed back by 2 Newton. So that this scale will read actually 1 Newton. Initially, it was reading 3 Newton when it was not in the fluid. Now it's reading 1 Newton. So collect the fluid that has come off of this container and weigh it, and you will see that is actually the missing 2 Newton. So that is basically that this force of the buoyant force is the same as the displaced fluid. Make sense? Okay, I want you to really put it in your own words. What is it meant by the buoyant force in here? Okay, I really want you to, I really want you to discuss this point in here. What do we mean by buoyant force in your own words? Okay, and explain how, and the word basically, a boat made out of steel floats. Okay, got it? Yes?
In the discussion?
Yes, please. Yes, please.
Okay.
Yeah, make sure that you have this understanding, because one of the things that you need to come up from this one is explain something like this one. How in the world, if you put, I mean, you take paper clip, for example, put it in a cup of water, and you will see the paper clip, which is made out of steel, actually sink. Okay. Whereas in here, you have a boat of it, and yet it doesn't sink, and it goes from goes through all of the oceans with no problem. Okay. Again, this is an explanation of the same principle in here. And so the buoyant force is the same everywhere, because as long as the difference in height in this case is the same, as long as the volume is the same, actually, it doesn't change. Because if this was 1 unit of pressure from the top and 2 units from the bottom, as you go deeper, for example, if there's 3 in the bottom, it's going to produce 4, so that the difference of the 2 of them stays. Let's say, for example, each one of these arrows is 1 Newton. So there is 1 Newton equivalent to force, okay, because you have to see how much fluid has been displaced for each and every one of this one. So the weight of the fluid. So it's going to be, for example, 1 Newton upward. It's still 1 Newton in here, because 4 minus 1, 3 is 1 Newton, and 5 minus 4 is still 1. So the buoyant force doesn't depend on how deep you are, okay?
Professor,
Yes.
when you were talking about buoyancy for that question, does that go in discussion chapter 5?
Yes, we are in chapter 5. Very good.
Okay, thank you.
So the key thing in here, this is in a nutshell basically what the discussion is asking, but please try to put it in your own words. Do not copy and paste, okay? You need to show understanding, okay? You need to basically put it in the clever words of your own choosing. Again, this is examples of it, on which of these blocks submerged in water is the buoyant force greatest. Now you need to know a little bit of the density in here. Ask yourself which one is denser of all of these objects, okay? Obviously, lead is super dense. Uranium is actually dense too. Out of these 3 metals, this one is about 2.7 kilogram, no, 2,700 kilograms per cubic meter. So it's still more than 1,000, more than that of the water, okay? But it's actually very close from the water versus all of the other metals. So this one is going to be bigger. So if you want to have 1 kilogram of lead, might be this. Another kilogram of uranium might be this. But if you want to produce the same kilogram of aluminum, you need a bigger volume, much bigger thing, because all of this is 1 kilogram. This is 1 kilogram. This is 1 kilogram. So in order for you to produce the same 1 kilogram for this different mass, different densities, you need different volumes, okay? Because 1 kilogram divided by smaller volume gives you a bigger number than 1 kilogram divided by bigger volume, which is a smaller number, okay? So you need more aluminum to produce 1 kilogram. It's going to displace more water then, because it has more volume. Hence, it's going to experience more buoyant force. So the water, the first one probably will displace this much, the second one probably displace this much, and the third one will displace this much, okay? Therefore, the aluminum is going to experience the higher buoyant force, because it doesn't care how much the object is, it cares about the space it occupies, how much space you're going to remove from the fluid, okay? Does everybody understand this question? Why it's aluminum and not the others? some of this, you really have to consult the tables for the densities to understand these questions. And this is basically the known value for it. It's much, much lower density than a lot of the metals that we encounter, okay, for the aluminum. That's why it feels light when you are in the kitchen. Try to pick up a steel, for example, or an iron-made cooking, what do you call it, pan, versus that of aluminum. You will see which one is lighter. Is this intuitive enough? Yes? Okay. I already talked about this one in here, this example of the iron. This is actually part of the discussion point in here, why the boats float, okay? So this is the same thing as I mentioned about. If you are not sure, just come to this point or look at the book in here and this the question, okay? So all of these are questions basically related to this one in here. Again, this is the principle in here, the basically using this principle to move the fluid. So we're not going to spend a lot of time on these things in here. Again, this is one of the saddest stories in physics, actually, is this one, okay? He's trying to understand the pressure on the microscopic level. People, before Mr. Boltzmann, they knew about the pressure. They knew about the volume of fluid. If you increase its pressure, for example, and keep the volume the same, its temperature increases. If you increase its volume and keep the pressure the same, the temperature increases. If you keep the pressure the same, if you keep the temperature the same and increase its volume, the pressure drops, and vice versa. So these laws were known, and people put them and summarize them in some relationship for the gases called PV equal to nRT, which is a gas law, basically. That's how they described it. Mr. Boltzmann, before the discovery of the atoms, came up with an explanation. He said that if I assume the air, for example, is filled with tiny particles, I can explain what this pressure is, and he came up with an immaculate interpretation of that law. We're going to get it when we get into heat and thermodynamics and stuff like that. But the point being in here is how often this particle hit the sides, basically, of the container where they are in. That is what the pressure is, okay? So it's the force with which, or the impulse, if you guys remember the impulse, which is imparted to the walls of the container by these fast-moving particles, okay? So they hit it once, they give it a nudge. Of course, it's not going to move because it's supposed to be rigid. They go back and hit somewhere else and come back and hit it again. It's the buildup of this motion that gives you the concept of pressure. So this is basically in pressure in gases. And how fast these objects move will give you higher and higher pressure. That's why when you increase the temperature in here, because these guys will be moving faster and faster with higher temperatures, the pressure increases, okay? If you put them in a container and fix that container so that the volume doesn't change, just heat it up, turn on the oven, and you see the temperature rise. This one starts to move faster and faster, builds up pressure. And that's actually the pressure cooker, how it works too, okay? In the pressure cooker, the first thing you do is you seal it. If you don't have one at home, you can actually go to the store and see it. They have a very good seal in there so that it doesn't come out. And then you put your soup inside and you turn on the heat, okay? Now the temperature is increasing, which means that the solution inside starts to move faster and faster, build up higher velocities because of the higher temperatures, and that increases the pressure, basically increases the force with which they impact the walls, basically, of the container. And if you release the gas, you will see it escaping at tremendous speeds with high temperatures because of that amount of heat that builds up. Okay. So again, a relationship between pressure and density. Again, the density in this case, if you increase the pressure, another way of doing it also by basically putting more and more pressure, then in this case, of course, the density increases too. So the density and the pressure, and the density is the amount of stuff in a container. Okay. It's reminding me that I have another class that's going to start soon. Don't worry about it, okay? Anyway, so again, double density of air, doubling the amount of air, decreasing the volume of to half. So again, if I have a piston in here, changing the volume also will amount to changing the density. Remember again, the density is mass over volume. So if I have a piston that is free to move and I have a container in here and I have a gauge in here reading the pressure, obviously if I make the pressure higher, if I make the volume less and less, what happened in this case, the volume shrinks, and when it goes down, you're dividing by less and less numbers. So let's say, for example, the volume shrinks by a factor of half, then the mass is the same. You didn't put more gas inside or remove, or this is hermetically sealed. I mean, not only that, but it's sealed so that there is no escape for the gas. It doesn't go anywhere. So when you change the volume, in this case, the density increases because you're dividing by a smaller and smaller number. Actually, more stuff is contained. I mean, more compact stuff in this case. And remember, density measures the compactness of stuff. Okay, and this is Boyle's law. This is exactly what I was talking about. Increased pressure, P goes up, and the volume must go down if in this case the temperature is maintained the same. Okay, because the initial pressure, so if this number, let's say for example was, let's give an example in here. Let's say for example, let's give a practical example. 2 atmospheric pressure, and this volume was 1 liter, okay? I know that they are not in SI units, but let's say for example, 2 times 1. So if the pressure now has increased by a factor of 2 to 4 atmospheric pressure, so put more atmospheric pressure, the volume needs to shrink accordingly in here, so that 2 times 1 is 2. This one has to go by a factor of 1/2 liter. So you take a liter and you shrink it by a factor of half, the pressure will double, okay? Because the volume went down. So this is Boyle's law. This is part of the big law that, that is the gas law, basically. Again, this explores the same ideas in here. And this, we mentioned it earlier, that the atmosphere actually is a fluid. And if you take a container and you empty it from the, that's the Magdeburg, basically, hemispheres, you will see the pressure actually. You need a tremendous amount of force to open them, actually. And this is the example in here with these hoses trying to open them. And you need that much force just to show that there is tremendous pressure in here. Again, it's the weight of the fluid that is above us, which is in this case air, okay? And on a square meter square, this is how much pressure is, 101,000 pascals, or 101 kilopascals, and kilo stands for 1,000. So 101,000 pascals, or roughly on a square meter, there is 100,000 newtons. 100,000 newtons is about what, 10,000 kilograms. It's about 20,000 pounds. Can you lift a 20,000 pound? No. The truck, for example, a semi truck is about that much weight. Can you lift it? But you are lifting as much as it is right now as we speak. That's exactly what you're doing. We're adjusted to it. That's basically how we are right now. This pressure, if it's underwater, remember, the pressure depends on the depth of the water. And because I know the density of the water is about 1,000 kilograms per cubic meter, okay? And I know this is the density, and if I multiply it by G, and G is 10 meters per second, if you guys remember. So 10 meters per second squared, I'm sorry. And if I go a depth, let's say, for example, of 10 meters in the ocean, there is a formula that we saw previously that says the pressure in this case is going to be the weight density of the water, which is 1,000 kilograms per cubic meter times 10 meters per second That is exactly what the weight density is, okay? Times the depth, and the depth is 10 meters. If we go 10 meters, 10 times 1,000, that's 10,000, times another 1,000, another 10, that's 100,000. In other words, if you go just 10 meters or 32 feet under the water, you're going to feel another atmospheric pressure in addition to the atmospheric pressure that is coming above the surface of the water. If you go 100 meters, so if you go 10 meters, you're going to experience another atmospheric pressure, another 100,000 basically pressure. If you go 100 meters underwater, you're going to experience 10 more atmospheric pressures with these numbers, in addition to the atmospheric pressure for a total of 11 atmospheric pressure. At that point, the atmospheric pressure will be negligible. You don't worry about it. If you go 1,000 meters or a kilometer under the ocean, this is about what, 300? No, this is about 300 feet, yes. And this is about what, 3,000 feet? So this will be 101 atmospheric pressure. So if you go 10 kilometers, which is roughly the depth of the biggest ocean, at least in the Pacific Ocean, you're going to experience what? 1,000 atmospheric pressure, pressure that will crush you for sure. So without proper attire, even going 20 meters, you're going to experience a lot of pressure, okay? Proper suit for it. Which brings me to a point in here, and I know we are midway in the slides in here. You have the fish in the ocean that can live in depths that are much more than 100 meters. We know that for a fact, okay? But they survive there. This tremendous pressure. How does the fish do it? This is tremendous pressure. It's going to crush us. Take anything in here. Take the elephant, if you like, and put it in that depth of, let's say, for example, 500 meters, 1,000 meters. They will be crushed no matter what, even you and I. But the fish is not crushed. Can you guess why? Their bodies are used to it. In what sense? You're right, Alyssa, but in what sense? Let me tell you the secret of the fish, okay? What they do, they breathe the water, okay? They take the water in, so their internal pressure is the same pressure as outside. So their bodies do not feel the difference in pressure. The only reason why we'll explode ourselves on Mars is because there is an imbalanced pressure between our bodies and outside the atmospheric pressure of Mars. That's why we explode. The only reason why we'll implode under the tremendous pressure of the ocean, ourselves, or that of Venus, is because, again, there is an imbalance. There is more pressure outside our bodies than that of our bodies, because our bodies are just basically used to the 1 atmospheric pressure. So if we land right now in Mars, we're going to be crushed, basically, because of that. We're going to implode, okay, the opposite of exploding. So how can we survive then the ocean, this much depth? All we have to do is breathe the water. Can we do it? Alyssa, that's your solution. So if you want to survive that much depth, all you have to do is just breathe the water. Do you think it's a good solution? No. So that's really the solution. That's how the fish does it, okay? So there is a balance of pressure. So as long as that pressure is, this is my depiction of a picture of a fish. So because it's taking in and out basically the water, it's breathing it. So the pressure inside and the pressure outside is good. So it doesn't implode or explode, so it's fine, okay? So the deepest that you're going to be able to actually use air to pump it out naturally is 10 meters without an artificial pump. So if somebody gives you a straw and tell you, how much fluid can you drink off of a well? As long as the well is less than 10.3 meters to be more specific, less than 32 feet, you can use the straw and suck basically the fluid, the water from it, okay? But if this well is much deeper than 10.3 meters, no matter how hard you try, you're not going to be able to get any water into yourself, because you're not going to be able to use the atmospheric pressure to lift that air to your advantage. The only reason how we basically drink with a straw is basically by doing that. We suck on it and it's going to go through us, because we're using that actually difference in pressure between this depth of fluid and the atmospheric pressure to our advantage, okay? So that is basically in a nutshell. So if you are on Mars, for example, and you happen to survive the atmosphere and you remove your mask and you're breathing the air, for example, of Mars, and you try to drink this coffee, you cannot, because there is a lot less atmospheric pressure on Mars than on Earth, okay? So that's basically in a nutshell what this whole slide is. Again, okay, we're gonna stop in here, because the mechanical pumps, they will help actually in making this happen, okay? And we're going to hopefully catch up somehow, okay? Because we have the review of the exam on next week, okay? And hopefully we still have quite a few things to do in fluid mechanics, and also the next 2 chapters that are actually due in this exam, okay? Okay. I will see you guys. Please, I know that there are several assignments that are due, so please take care of them, okay, this week before we get ready for the exam. Any questions before I stop the recording?
How many items were there for this chapter 5 discussion? Just one?
Yeah, just the one, yes. Okay. Thank you. Okay, I'm gonna stop the recording and I will see you guys Thursday. And be safe, please. Thank you.